Hi all. This video is a brief overview of data science and machine learning, and in this video, without getting into a lot of details of the various techniques which people use in data science and machine learning, we will try to understand at a broad level what these two terms mean and what kind of implications they have for science, engineering and lives in general. So the word data and the word science have always been in existence. Similarly, the words machine and the words learning have again been in existence for many centuries. But coming together of these words is a fairly recent phenomena, maybe over the last few decades, and that has led to very unprecedented developments in science, engineering, and has impacted our lives in ways that perhaps we could have never imagined. So let's try to understand what does it mean when data and science come together and when machine and learning come together. So before getting into machine learning, let's take a sneak peek into data science and understand how is data science different from just data and just science. And in this case, is 1 plus 1 equal to 2 or 1 plus 1 equal to 11? As it turns out, it is the latter case, that 1 plus 1 in this case is 11 because the coming together of data and science has led to absolutely unprecedented advances, which are totally unimaginable. So data earlier was available in the form of various kinds of measurements which human beings did using various tools, and then they analyzed it on their own using their sensory organs. And all the discoveries that have happened in science, be it Newton's discovery of gravity or Kepler's laws and many other important scientific discoveries have all happened based on analysis of lots and lots of data. But when does data become science? So that boundary between data analysis and data science is not absolutely clear. There are kind of different opinions on what is called data science and what is not called data science. But roughly speaking, one can say that data science is basically about use of data to do statistical modeling of various phenomena in order to do automated predictions. So don't take this as a bookish definition of data science because it is not, and there may be people who don't even agree with this idea. But this, I think, gives broad level understanding of what data science is primarily about. So earlier, maybe a century back, or maybe I would say even 70 years back, data was primarily used for doing analysis using various kinds of mathematical tools and techniques, and then they were analyzed by human beings using human intelligence to draw inferences about the world. And that's how we have various kinds of laws and models that have been developed. But over the last few decades, because of unprecedented developments in computer science and computing technology, including the development of the semiconductor chip, we have been able to automate a lot of this process. So, in many areas now, human beings have kind of taken a backseat, and computer algorithms have been able to do a lot of this modeling on their own and be able to make fantastic predictions about the future. A very important point to understand over here is this word statistical. Okay, so when a human being does a modeling task, it may be statistical, it may not be statistical, because human cognition has access to many other ways of modeling the world around. For example, many laws of classical mechanics are not statistical in nature. They are kind of deterministic in nature. But because a computer has a limited range of things it can deal with, so far the models that we have been able to develop in the context of data science are all statistical in nature, because they use lots and lots of data to come up with the model, and their models are inherently probabilistic in nature. So what that means, we will understand in due course of time as we make more videos on more topics. But for now, I think it is important for you to understand that these models are inherently probabilistic in nature, that they make probabilistic predictions about what are the possible future outcomes about the phenomena that this model is dealing with. So now, one more important difference that takes data science to machine learning is that, so when we talk of data analysis, okay, so what does data analysis basically mean? Is to do curve fitting and to find some patterns in your available data. So let's say, for example, you have some kind of graph which is, let's say, some y versus x, where y and x represent some quantities in real life. We don't need to worry about what those quantities might be, but just that they are some quantities that have been measured using a physical instrument. So now let's say you did some measurement and you found that the points y and x lie on this line, and let's say that the underlying function is something of this form, which through some other source. Maybe the equations which govern y and x, and so from there that this should have a curve of this kind. But any curve is governed by some parameter. So let's say if we take a linear equation, then a linear equation is given as y equal to mx plus c, and this has two parameters. One is your m and one is your c. And now let's say if you take a quadratic equation, you get y is equal to some a2 x square plus a1x plus some a0. So these are a2, a1 and a0 are again some parameters which you don't know of. So conventional data analysis has been mainly about finding these parameters of known functions. So usually we knew what function we had to fit, or if we didn't know a priori, we could figure that out by visually inspecting our data, and then we would try to fit a certain curve to the available data to find out these parameters. So this kind of an analysis is usually called data analytics. Usually, again, there can be different opinions about it, but broadly speaking, this can be called as data analytics. But when we get into the domain of data science, we are making a big leap in complexity. And when we are in that domain, we no longer know which function our data will fit to. Okay. So if you really know which function your data is going to fit to, then you are mainly doing data analytics. But you kind of get into the domain of data science and machine learning when you don't really know what kind of function your data will fit to. So now you may ask, okay, if I don't even know the function that my data will fit to, how is it even possible for me to do any kind of computational analysis? And that is the brilliance that machine learning brings along with it. So this is why machine learning is so powerful. It is also its drawback, but it is that drawback which also gives it its power, which is that without completely understanding what the machine learning model is doing, nowadays many people even call it like a black box. But despite knowing all the details, we are still able to do a lot of data analysis and make really amazing predictions, which we may not actually fully understand. So how does that happen? Think of a box of Lego pieces. Each of those pieces is actually very simple, but you can compile all of them into very different kinds of shapes and sizes, which you can be very creative with, something that you have never even seen with your own eyes, you can make using Lego pieces. So each piece in a Lego box is very, very simple, just a cuboid with some spikes to fit into each other, and then by combining them in different ways you can make whatever it is that you want. Machine learning is something like that. So it works on similar principles where you have the small computational elements of various kinds, which we will explore more in future videos. And then the beauty is that you can combine these small computational elements in many different ways to form very complex structures which have unimaginably great power. And the amazing thing is that it has been mathematically proven that these small and simple computational pieces can be combined to mimic any arbitrary functional relationship between the input and the output. And this is what gives machine learning its power, that you can take these very, very simple computational pieces which are perfectly analytical, which can be understood perfectly well, but when you combine many of these pieces, they start behaving in ways that you have never before imagined. And that is precisely what machine learning is all about. So in other words, machine learning is an advanced version of curve fitting, but with the very important difference that in machine learning, you actually don't know what the curve is. So it is curve fitting without actually knowing the curve. So this may sound very crazy and very counterintuitive, but essentially that's what it is. Now you may say that, okay, that every algorithm actually follows a fixed set of steps, which we all know because we have the code in front of us. So how is it that we don't know the curve? So when we say that we don't know the curve, what we mean is that we don't exactly know its behavior, right? So we have the code in front of us. So technically speaking, we have full information about what the algorithm is doing, but because of its inherent complexity, but because it has so many different parts which have been combined together, that we don't really know what it is actually doing and what kind of shape the curve has. So that is what makes machine learning so amazing and so interesting and also so powerful. And it is precisely because of this reason that machine learning algorithms are called intelligent. So all of us have heard the words AI, artificial intelligence. And so this is why a machine learning algorithm is called intelligent, because if you exactly know the steps that a person is doing to solve a problem, then it is unlikely that you will call the person intelligent, because you exactly know what is being done. But intelligence comes in when there is an element of surprise. That when you gave a problem to a person or a computer, which you maybe didn't think the computer could solve, or maybe you couldn't imagine the way in which the computer has solved it, then you would say that okay, maybe this computer or this human being is intelligent. And that is precisely what is happening over here. So if you knew the curve that the algorithm is fitting, then you would not call it intelligent. So a lot of data analysis has happened in the past using curve fitting, and none of them is called intelligent. But now, because you do not know the curve, because very, very simple computational elements have been combined in amazingly different ways, and they are doing things that you could not have predicted, is why you are calling this machine learning algorithm as having artificial intelligence. But it is important to know that this form of artificial intelligence is only weak AI. So there are two kinds of AI. One is strong AI and one is weak AI. And this kind of AI using machine learning algorithms to solve complex problems is called weak AI. So what is strong AI? Strong AI is a system which has self-awareness and a conscious experience like human beings do. We currently have absolutely no idea how to create such a machine, but at least conceptually, we would like to do it someday. Whether we succeed or not is another story altogether. So, now when we talk of machine learning, it comes in many different varieties. There are many different kinds of machine learning algorithms that one can use, but broadly speaking they can be classified into three different categories, and we will cover all these three categories in this course. So the first category, which we are also going to begin with in this course, is what is called supervised learning. So a simple example of supervised learning is, let's say you are given the image of an animal and you want to find out whether it's a dog or a cat. So what do? You collect lots of such images of dogs and cats and you label them as dog and a cat and you feed them into your machine learning algorithm. And now once your machine learning algorithm is trained, you take a new image and then you feed it into the algorithm, and the algorithm will tell you whether it is a dog or a cat. And this is an example of supervised learning because the algorithm has learned using a certain tags which you have provided. So the images that you gave to the algorithm had the dog or cat tag associated with it. So the input is the image and the dog/cat is the output. So in this case, when the training data set, so when you train an algorithm using a certain data set, that is called the training data set. So when the training data set has specific labels, then that process is called supervised learning. And this is, very popular in, face identification, and many other problems like handwriting recognition, and so on. The second type of machine learning is what is called unsupervised learning. So what is unsupervised learning? It is exact opposite of supervised learning. That is obvious from the name itself. So in unsupervised learning, we do not provide any kind of output tag to our machine learning algorithm. So let's say you have a company, let's say you are the general manager in Amazon and you are in charge of predicting future customer behavior. So what do? You collect the sales data from the Amazon website. Whenever you make a purchase on the Amazon website, the website collects a lot of data about you, and that's how they have been able to service you so well. So now you take all this data, you don't exactly know what kind of customers you have on your platform. So you take all this data and try to segregate the customers into various different categories without actually knowing a priori how many such categories may be there or what kind of categories may be there. But you just take that data and try to find some patterns and identify the various different categories. This is a example of unsupervised learning. We will again see more examples in the future, but this can be one example that classifying customers in various ways. The third kind, which is perhaps a lot more recent, but again very, very powerful, is what is called reinforcement learning. So reinforcement learning is what has made all these driverless cars and robotics and many other kind of automation systems possible. So reinforcement learning is in some ways similar to supervised or unsupervised learning because essentially finally all of these are algorithms. But it is also fundamentally different from supervised and unsupervised learning because reinforcement learning is about learning to perform a certain task. It's like when a human being learns how to dance or to act or to ride a bicycle or to drive a car. that is a kind of reinforcement learning where you are not trying to find patterns in a data set. You are not trying to find a function that will map an input to an output, but you are trying to learn how to perform a certain action. For example, you must have heard about the AlphaGo algorithm, which has been able to learn how to play Go and defeat even the world champion. That is an example of reinforcement learning because the algorithm has learned to perform a task, which was to play a certain game and win it. So these are the three primary kinds of machine learning algorithms which we are also going to study in this course. As I mentioned that machine learning is a kind of a weak AI system. So now the moment we talk of artificial intelligence, we are reminded of intelligence and then we are reminded of human behavior. And it is true that initially when machine learning started, one of the goals was to mimic human behavior because humans were considered and are still considered to be the most intelligent beings on this planet. And so the goal of machine learning was to see that can you train computing machines to behave like humans and to do things that humans are capable of doing. And in this quest, the first and the primary techniques were to try to mimic the way the human brain works. So a lot of the early machine learning algorithms were indeed inspired by the human brain. But over the decades, it was found to be not such a good strategy. And now people, who work in this community don't really even bother about how the brain may or may not work. And the current ML algorithms have taken very divergent trajectories and have very little or no resemblance to how the human brain or the human body actually functions. So now when we talk of artificial intelligence, it is not really trying to mimic human intelligence, but has taken a trajectory of its own and has a life of its own. So now one question that often crops up in this regard is that is machine learning equal to AI, or is AI a subset of machine learning, or is machine learning a subset of AI? Okay, so we have three options, which is that ML is equal to AI. I'm writing WAI because I want to emphasize that we are only talking about weak AI and not strong AI. So one option is that ML is equal to weak AI. The second option is that ML is a subset of weak AI. And the third option is that weak AI is a subset of machine learning. Now this again does not have a very clear answer and different people in the field may have different opinions depending on what is defined to be machine learning and what is defined to be weak AI. But I would like to say that weak AI is a subset of machine learning algorithms in a broad sense. And why is that so? That is for the simple reason that when we are talking of artificial intelligence, we are obviously referring to machines because biological systems have real intelligence. So of course an AI system has to be a machine, and anything which is intelligent has to have a learning component, because if everything is hard coded as an algorithm, then it is not really learning anything. It is already hard coded. So if it has to perform an intelligent operation, means it has to surprise us by doing things that we didn't expect it to do, then there has to be a component of learning. And if you have a machine which is learning, then obviously you are in the domain of machine learning. But there can be many machine learning algorithms which are not AI, which means that they are not really intelligent, although it's a machine and although it's learning something, but it is fairly rudimentary. It is not really a kind of AI. So in that sense, machine learning is much, much broader than what can be called AI. But you cannot have AI without machine and without learning. So to me, the only option is that weak AI is a subset of machine learning algorithms. So now the holy grail of machine learning. Okay, so earlier, as I said, the holy grail of machine learning was to mimic human behavior, but that has now changed. People have realized that biological systems and the human brain work in ways which are very different from what can be easily captured in an algorithm. Each of these have their own advantages and disadvantages. And so, in order to leverage the full power of computing systems, machine learning community has kind of moved on from its initial goal of trying to mimic the human brain. So now, what is the holy grail now, or have we totally given up on any such common objective? The answer is that yes, we do still have a holy grail or a common objective in the machine learning or AI community, and that goal can be summarized in one word, which is generalization. So what does generalization means? So currently, machine learning algorithms are very good at doing a particular task. Okay, so if you train a machine learning algorithm to identify dogs and cats, it is very good at identifying dogs and cats. But if you give it the image of a tiger or a bear, it of course cannot do so. So that has been a major challenge for the machine learning community, that can the same algorithm which was good at identifying dogs and cats can now also be good at doing other tasks for which it was not specifically trained on, right? So meaning that if a machine learning algorithm is trained on a particular problem or on a particular scenario, then it is generally found to be bad at other scenarios, and you have to again do the training once again from scratch. And that is a problem that the machine learning community is trying to solve. So that is one kind of generalization, where the generalization is happening over different scenarios. But there is a simpler kind of generalization that I would say has, we have made large progress in that domain, is generalization over other data sets. So for example, even if we take the problem of dogs and cats, and if you have, let's say, trained your machine learning algorithm over 1,000 images of dogs and cats, it may still turn out that the algorithm may fail when you give it a new image, even though the new image was of a dog or a cat. And that is because machine learning algorithms essentially try to capture patterns in the training data set that you have given them. And if the new image does not have those same patterns, then the algorithm will completely fail. So now, without getting into too many details, let's try to understand how does this generalization over dataset actually work. So again, let's say that we have some x-axis and some y-axis, and we have some, let's say, data points that have been given to us, which have come from some kind of measurement that someone did. Now there are various ways in which you can fit a polynomial curve to this data set, let's say. So the simplest case, of course, is that of a straight line. So if you just take a straight line and if you try to fit it to this curve, so let's say you get a curve like this. Now of course this straight line will have a large error because many data points are actually quite far away from this straight line. Another thing that you could do is to take a higher order polynomial so that the line actually passes through all these different points which you have. So now that would be a very, very wiggly line. And the problem is that if you now have a new data point, which was, let's say, over here, then although your wiggly red line was very, very accurate while fitting to the training data set, but it would miserably fail when it comes to testing over the new data point that you have. And the problem with the blue line was that it was miserably failing to even fit over the training data set. So, that was a bad choice to begin with anyways. This kind of fitting is what is called underfitting, where you have not even tried to fit your curve to the training data set. And this other kind of fitting is what is called overfitting, which means you have overdone the fitting. You have taken a function which was too complex and which did a great job of fitting over the training data set, but it did a miserable job of fitting over the testing data set. So, in order to have a machine learning algorithm which gives reasonably good accuracy over both the training set and the testing set, you have to do a balance between overfitting and underfitting. And the way to measure whether you are doing underfitting or overfitting are these two quantities, which are called bias and variance. So this one has a high bias because it is very different from the actual function, and this algorithm has a high variance because although it is fitting very well to the training data set, but it is very wiggly in nature, and that is why the curve is varying a lot, and that's why it has a high variance. So your objective of a machine learning algorithm which has to generalize well over the testing data set is that to find the balance between bias and variance. Neither of them should be very high. A moderate bias and a moderate variance is what an ideal machine learning algorithm is all about. So this is how you generalize over other data sets. Now let's try to understand how do you generalize over different scenarios, because that's a more complex problem. So when I'm talking about different scenarios, as an example that I gave, that if you have trained your algorithm over dogs and cats, can you use the same trained algorithm to differentiate between tigers and lions? And usually the answer is no. So how do you then do it? So as I said, this is a very complex problem, but the way people have solved it is by an idea called embeddings. So a good analogy to this idea of embeddings is that of a mixer juicer grinder that you see in your home. So a mixer juicer grinder has the same basic machine, which is basically a motor, and then by using different attachments you can convert the same machine into a mixer or a juicer or a grinder. And that is basically how these embeddings work. So what these embeddings basically do is that they learn some general rules that apply to a very large set of data set from the problem that you're trying to solve. So for example, if you are talking about image processing, then you can learn properties of a very large set of images to form your core algorithm, and then you can stack a few more simple computational elements on top of that core in order to modify that core to perform various different kinds of functions. So this is exactly like the analogy which I just gave you, that you don't need to train the entire machine learning algorithm for your new task, and you only need to train a few additional computational elements. So for example, in the dog and the cat problem, so let's say you have a machine learning algorithm which you have trained for a dog and a cat. If you do it using this idea of embeddings, then if you want to use that algorithm for classifying tigers and lions, you do not need to train the whole algorithm again, but you only need to train a final few computational elements. So basically the idea of embeddings has a core plus few additional ML elements. So this core is basically a common core, And it is these additional elements that change as per the specific problem. And this idea is what gives deep learning the power that it has. So we will see some more details of this deep learning later on in future videos. But essentially this is the idea that they follow, that they have a common core which has been trained over a very vast and diverse data set. And then by adding a few additional ML elements, you can use that algorithm to do a very wide variety of machine learning tasks, and you do not need to train the entire algorithm from scratch once again. So this was a brief introduction to data science and machine learning. I hope it made sense to you. In the future videos, we will now take up specific concepts from data science and machine learning and learn all of its details. So stay tuned and stay connected.